We ended the previous lecture with the insight that Kolmogorov complexity in its plain version as we first defined it has some drawbacks. In this lecture we will now look at a variant of Kolmogorov complexity called prefix-free complexity, which aims at overcoming some of these problems of plain complexity. So if you recall from the previous lecture, we were trying to show that the complexity of a pair, of a coded pair, does not exceed the sum of the individual complexities in the string. In other words, we wanted to show that the complexity of the pair, sigma tau, does not exceed the complexity of sigma plus the complexity of tau. But the problem here was that if we have two programs, one for sigma and one for tau, and now we're trying to build a program for sigma and tau together by just concatenating the two. So we have P and then Q, and then we just concatenate the two strings. And assuming that both P and Q are shortest programs for their respective strings, we cannot, so then this string here would have combined length P plus Q, so complexity of sigma plus complexity of tau, but we cannot use this combined string of length complexity of sigma plus complexity of tau as a program for the pair, because now if a machine starts scanning here, where does it recognize that the program for P ends and the program Q starts? Right? The machine itself will just see one big string, right? So where does it kind of make the cutoff or split the two strings here? So it cannot see that. Well, how do we get around this problem? Well, solution here we consider is that we require our machines to have an extra nice property which makes exactly this possible, what we just described. Those machines are called prefix-free, and the definition is just, well, if a machine converges on an input P, then it must diverge on all extensions of that string P, right? So in pictures, so if a machine converges, let's say, on string P, then if we have any extension, right, of this P prime, right, so then on this string our machine would not converge. And if you look at this now a little bit more careful, you will see that this actually means that no two converging inputs are initial segments of each other, are prefixes of each other. So that's why they're called prefix-free. So just to repeat it once more, prefix-free machines means that whenever I have a converging input, nothing that extends this converging input converges. So for this as an input of the machine. And if you recall from the section from the lesson on measures, we've already encountered prefix-free sets there in connection with defining measures and so on. And here we encounter this again, and we can say that a prefix-free machine is just a Turing machine whose domain is a prefix-free set of strings. Right? That's another way to put it. So why does this help us with this problem here that we described first, that we encountered? Well, now think of it. If our machine is prefix-free, then we can now start scanning our input here bit by bit. We know that the machine will converge on at most one input, right? It will converge on at most one initial segment of this whole string here, right? So, and if that's found, I know, well, here it converges, well, that must be my P. Then I'll just run it, and then I'll run the machine again, the universal machine again, on that remaining bit. Okay. So we now define this variant of Kolmogorov complexity, and this is based now on prefix-free Turing machines. So the idea is similar to the original definition, which we also now refer to as plain Kolmogorov complexity, is to use a universal prefix-free machine to make it a rigorous notion, right? A universal prefix-free machine is just a machine that is universal among the prefix-free machines. So what does this look like in detail? Well, first we note that there exists an effective listing MD prime of all prefix-free Turing machines. Well, the reason is we can just modify an enumeration of all possible Turing machines, so that if we encounter a Turing machine whose domain is not prefix-free, we change it to a prefix-free machine. So assume we're kind of enumerating a machine, a certain machine ME at the moment, and then we kind of look, where does it converge? What does its domain look like? Well, so far it looks prefix-free, but then suddenly we see, oh, here is an extension that violates prefix-freeness, right? Because now the machine converges on this string and the extension of this string here. Well, in this case, we just change the definition of this machine, right, as we enumerated, and just say, okay, it does not, the new machine, the altered machine, does not converge on this pink string anymore. We just make it undefined there, and thereby preserving the prefix-freeness. We can effectively do this because we can effectively catch if something like this happened. We'll see it in course of enumerating all the inputs for which a given machine converges. Now, if we have such a listing, MD prime, right, we just define U prime to be to do the following. So U prime is defined on the following inputs. It's defined on the inputs of the form 0 to the D, 1P, right? And then it parses the input and performs or emulates the prefix-free machine MD prime on input P. This definition is a little bit different from the definition of a universal machine, non-necessarily prefix-free. Well, the reason is we want this machine to be prefix-free, right? And that's why we give it this special input format here. So what does this look like now? Well, what does U prime do? Well, it first, as an input, gets the length as a code, the index of the machine it's supposed to emulate, right? As in the form 0 to the D, and it takes a 1. And then above here it gets the program now that is fed to the machine it emulates, right? But since we keep it in this special format, right, so a different machine will be coded like this, right? And then the program for it. And you'll see, since each of the machines MD here is prefix-free, so above in this cone here, everything that converges there is prefix-free. And since we kind of stack them up in this prefix-free way, U prime itself is still a prefix-free machine. So we see that from this that U prime is indeed prefix-free, and it clearly can also emulate all other prefix-free machines. So we now fix a prefix-free universal machine, and then based on this we can define prefix-free Kolmogorov complexity as just the complexity, the plain complexity with respect to this universal prefix-free machine, as before. So we denote this now by the letter K instead of the letter C to distinguish it from plain complexity. There's an invariance theorem that says that this complexity does not exceed any other prefix-free complexity, so defined for complexity defined on the basis of a prefix-free machine by an additive constant. And this is proved just like in the plain case. And as I already indicated a couple of slides before, now we easily get that this prefix-free complexity is subadditive. That is, the complexity of the pair does not exceed the complexity, the sum of the complexities of the elements of the pair. And we can now see this. Well, suppose P and Q are programs for the universal prefix-free machine for sigma and tau, respectively. Well, then we can construct a prefix-free machine M prime such that M prime on input, the concatenation of the two outputs the pair. Right? Okay, so how does this work? Well, and as I already indicated before, well, we get as an input one string, right? And we assume now, of course, that our machine tries to find or assumes that this is such a concatenation, and hence it tries to find the point where it has to split the input into this P and Q pair. Well, using bootstrapping now, so it runs simultaneously on all possible initial segments, running one step at a time for each of those inputs. It tests every initial segment theta of its input to see whether the universal machine on this input converges. Right? But it's a prefix-free machine now, right? So U prime is a prefix-free machine. So it can converge on at most one of those inputs, if it does converge at all. And if it does converge, then that actually must be our combination, right? And then we have found the program, we have recovered a program for sigma, and then we can just use the rest here as a program for tau, and hence this way produce the pair. Well, on the other hand, prefix-free complexity also has some drawbacks. It's technically a little bit more complicated, and that's one thing is indicated, or that indicates this, is that we no longer have this nice upper bound that the complexity of a string is at most its length, up to an additive constant, as always, of course. So this is no longer true. Well, what's the reason for that? Well, the reason is that the copy machine, remember, to show this, we just looked at a machine that copied its input to the output, right? And so MP of P is equal P. That's not a prefix-free machine. Right? That's not prefix-free. So that cannot witness that this is actually true, right? Because, yeah, as you easily see, this is not prefix-free. So how complex can a string get with respect to this prefix-free complexity? Well, we can try to implement a prefix-free version of the copy machine. We could define a machine M prime that converges only on inputs of this form, and on inputs of this form, so 0 to the length of P, 1P, right? Then it just outputs P. So in this sense, we code the length of the actual string that we want to output before the actual string, right? So in this sense, the machine first reads the length, right? Then sees, oh, there's a 1, that stops the encoding of the length, and then what I read after that, I'll just output. And by doing it this way, right, by putting a 0 to the P, length of P over here at the beginning, I make this machine, the copying process, actually prefix-free. Because as you see now, right, we have again, here is the initial coding of the initial segment, 0 to the P, and then there's the 1, and then we have all the strings, but only the strings of length P, right, for this is convergence. If we have a different length, right, then we first go, maybe a longer string, then we first go here, then the 1, and then all the strings up to here, right, and so on. So you see, this is a prefix-free encoding. So what is now the description length of P? Well, the length of this string is the length of p, right, plus 1 plus the length of p again. So the length, in order to produce p, we need 2 length p plus 1, which is within an additive constant, gives us the bound that the prefix-free complexity of a string is at most 2 times its length. So instead of just the length, we have here 2 times the length. Well, it seems there's quite a discrepancy between the two bounds, the ones that we had for plain complexity, which does not hold for prefix-free complexity, and our copy machine or prefix-free copy machine bound for prefix-free complexity, which is 2 times the length. So maybe we can do a little bit better. And we can indeed do better. I mean, it turns out that this coding, right, this prefix-free copy machine coding is rather inefficient. Right? We just need to make this copy machine prefix-free. But we can use any kind of prefix-free coding. So why not use, instead of using this 0 to the length of p1p, we could just give a shortest program for length p, right? Because our universal machine u prime, so u prime shortest program, but that's prefix-free, a prefix-free machine. So all shortest programs are in particular form a prefix-free set. And if we do this, we get the following theorem. The prefix-free complexity of a string is bounded from above up to an additive constant by the length of the string plus the complexity of the length of the string. And we will see later that this bound is indeed sharp. It also reconnects us with a different aspect of why plain complexity is sufficient as a measure of information. If you recall, when we tried to construct this counterexample to subadditivity for plain complexity, we exploited the fact that a string not only provides information through its bits, but also through its length. And that's really what is reflected here too, so through this upper bound. Because not only does it provide information through its bits, right? So assume we have a maximally complex string, then it will provide information through its bits, right, in this form, but it will also provide information through its length. So information through 1 bits and length. So it seems that prefix-free complexity actually takes care of both of these sides that we saw then, or drawbacks we saw when looking at plain's complexity. One was we cannot tell when an input ends, right, and another one starts. And the other one was we can exploit that a string can present information not only through its bits, but also through its length. And indeed it seems that those two things are just two sides of the same metal. So how do we prove this theorem now? Well, more or less as I already indicated, we consider the following machine. It's a prefix-free machine, M prime. And on input P, this machine M prime scans the input for a possible splitting. So a little bit like we had before when showing the subadditivity of the prefix-free complexity function. So we're looking for a splitting into two parts Q and R, such that when I input the Q part into the universal prefix-free machine, I get the length of R as an output. Remember, we always identify natural numbers now with binary strings. So again, we have this one input, big input P here. And now for this input, our machine M prime now starts scanning the initial segments here for a possible input Q, right? So that when I feed input Q into a universal machine, right, I get as an output, so U prime of Q, as I get as an output the length of R, so the length of the remaining string. Right, and that's of course the intention that was already indicated up here. Well, as in the argument before, since U prime is prefix free, there's at most one such splitting, right? Because U prime can converge on at most one of those initial segments. And if such a splitting exists, well, it's unique. And if it exists, we then say that M prime outputs R, right, this remaining string, and otherwise it lets it undefined. And then we just use the invariance theorem. If P is a shortest U prime program for the length of sigma, well, what does M prime then do? Well, then M prime on input P concatenated sigma outputs sigma, right? Because P is the shortest U program for length of sigma, so it just outputs that meets just this requirement here, right? So output is the length of the remaining string. Well, so that then outputs sigma, and hence we have that the prefix-free complexity of sigma, well, it's by the invariance theorem within an additive constant of the prefix-free complexity defined by M prime, right, of sigma. Well, but that's at most, well, we just produced a program for it, namely P concatenated sigma, right? So that's the sum of the length of P plus the length of sigma. But the length of P, right, P was assumed to be a shortest U prime program for the length of sigma. So that's actually the same as the prefix-free complexity of the length of sigma. So that's the length of P here. Okay, that's all. I want to finish this lecture with one important aspect that now the consideration of prefix-free machine makes possible, namely that of algorithmic probability. Remember, one of the questions at the beginning of this algorithmic entropy lesson, so the previous lesson, was, can we maybe define information content for individual strings based on a probability distribution? Right? So is there a probability distribution on individual strings that then we can just define as the negative logarithm of that distribution as our complexity? Well, there's something we could do now, because if you think of what do strings or prefix-free machines look like, so the domain, right, is a prefix-free set. So we know that this is how the domain, what the domain of a prefix-free Turing machine looks like. And some of those strings here may compute this actually, when we input it to U prime, may compute the same number. So suppose this is P, suppose this is Q, but they both compute, when I input it into U prime, compute a string sigma. So now the idea is, well, since this is a prefix-free set, if I start summing these strings, right, that for which the prefix-free universal machine converges, right, if I sum the length of these strings, right, sigma 2 to the minus length of P, where U prime of P converges, right, that's a number at most 1. So it's almost a probability distribution, but no, not quite. There's a little bit of defect in here. But anyway, so these, now I could take what is the probability of a string or better, the algorithmic probability of a string. Think of the following experiment. We just toss coins, right? We just toss coins, and we run the universal machine on a coin toss, right? And if it doesn't converge on my coin toss so far, so I start tossing coins, let's say, so this 0, 1, 0, 1, and so on, and we'll see if the universal machine converges for this. Well, if it doesn't, then I'll just toss another coin, and I extend my string. So if, however, I reach a point where this converges and outputs something, right, well, then I'll just output it. Now, what is the probability that this way I produce a specific string sigma? Well, it's just the sum of 2 to the minus length p over all p that for which the universal prefix-free machine outputs sigma. Right? And we could take this as the probability of the algorithmic probability of sigma. Right? So what is the probability that if I just by coin tosses generate a program that outputs sigma? So here is the formal definition of algorithmic probability. We define a probability distribution on strings the following way. The probability of sigma is just the sum over all 2 to the minus the length of sigma of p, where p is an input to the universal prefix-free machine that produces sigma as an output. So as before, you can think of it as kind of what is the probability that a random coin toss produces a program for sigma, right? And now we can ask, how is this p related to k? I mean, could it be that even be that k is up to an additive constant, the same as the information given by p, right, by this probability distribution p? Well, if that were true, what would have to be the case? Well, then we would have to have the following. Well, if you think of it, right, this would mean that, for instance, if there were a lot of long programs that would all produce sigma, right? All of these programs produce sigma, right? And they all produce sigma, right? That would mean that sigma has higher probability than any of those lengths, so sigma has a relatively high probability. But if then this were the same, for this to be hold, what would we need? Well, then the shortest program would have to be rather short, right? That would mean that if sigma has a lot of long programs, then it must also have a short program, right? That seems rather surprising, or would be rather surprising, but we will see that this is indeed true, and it leads us already deep into an area that then connects us back to what we started from the probabilistic or dynamical side, namely an area which we will need codes, and which is then called coding theory. So how to code information efficiently. And that's precisely what will resurface again when we try to prove this identity.